My name is Tom. I'm a solution architect specializing in networking. I'm joined today by Anup, Principal Product Manager from the EC2 team. And today we're going to cover hybrid networking on AWS. So I've been doing networking for the last 15 years, and throughout that time I've accumulated quite a lot of equipment in my house. Firewalls, routers, switches, or my wife likes to call them noisy junk. So I spend a lot of time finding the best deals online because it's quite expensive to get that gear. It's super heavy, so once you decide on what you're getting, you put it somewhere in your apartment and it's staying there forever. Eats up a lot of power, so that adds into your costs if you're running the lab. And then finally, it's super noisy, so I couldn't even use it when someone else was at home. So for the last 2.5 years, I've been with AWS. So I was super stoked I could migrate a lot of that stuff off to the cloud and get rid of all of my on-premise hardware. And I know a lot of you guys are going through the same process in your production. It's not always as easy. Plus, there might be reasons why you might still want to maintain some of the environments on-premise. So with hybrid connectivity, we want to make sure that connecting your on-premise environments back to AWS is as simple as efficient as possible. So today's session, it's 300, which means the level is a little bit more advanced. So we won't be explaining what a VPC is, what is a VLAN, but rather we'll focus on the building blocks of hybrid and then what architectures you can create using those building blocks. If you feel like today was a little bit out of your depth, you want to get the fundamentals, you can go and watch the NET317-R1 fundamentals session delivered by Steve Seymour and Alan Halachmi. Or if you feel like you want to explore some of the concepts we covered today, like the VPC or transit gateway or DNS, there are kind of deep dive sessions in each one of those topics. So what are we going to cover? We'll talk about how you can connect your networks to AWS using things like VPN, Direct Connect, transit gateway, VPC. Anup is going to talk about a feature we launched this week, Ingress Routing, that allows you to manipulate routes on the virtual private gateway and internet gateway. We'll talk about setting up your hybrid DNS between on-premise and AWS. And we'll finish off on remote access, so using Client VPN to connect your remote users to AWS resources and beyond. So what is hybrid? So probably a lot of you have set up a VPC. So if you have a VPC and the internet on the outside of your VPC, and you maybe deploy some resources inside your VPC and the subnets, some instances, you have an internet gateway, you can create a route through that internet gateway, and you can communicate with the internet. Maybe you have some other resources isolated from the internet, some backends. Very simple setup. But in this scenario, if this is all you have, you don't need hybrid. This is you being native on AWS. Hybrid comes into play where you have some type of environment on-premise, data center, branches, any connectivity from on-premise. That's where you need to think about what you're going to use to connect those environments in the best possible way to AWS. So let's start with the first building block, AWS site-to-site VPN. This is usually a really good starting point, very easy to set up, very quick to set up. You can usually have it set up in minutes. And typically, you would have all the equipment necessary to set it up already in place. So site-to-site VPN is a managed VPN offering from AWS where you get 2 VPN termination endpoints on the AWS side. And by endpoints, I mean public IP addresses. And they will be deployed in different availability zones. So when you're setting up your VPN tunnels, those tunnels would be 2 tunnels, and they would go to 2 different availability zones. So if there's an AZ failure, you still have another tunnel to get to your resources. Protocol-wise, standard IPsec, AES 256 encryption, SHA-2 for hashing, latest Diffie-Hellman groups for key exchanges. It also supports aggregation 2 and NAT traversal, so if you have a NATing device somewhere in the path, the VPN will still establish. And then finally, price-wise, it's charged per VPN connection hour, plus data transfer charges. So when you set it up for the first time, you have 2 options. So you can set up your VPN as a static VPN or as a dynamic VPN. So let's compare the 2 very quickly. From a configuration side, a static VPN can be policy-based or route-based. Dynamic can only be route-based. And the difference here is when you set up a policy-based VPN, you create a policy. Usually it's an access control list that defines the interesting traffic that you want to encrypt before sending it to the other side. Whereas a route-based VPN is when you have a logical connection that is always encrypted, and anything you route through that connection, through that interface, is always going to get encrypted and sent to the other side. Routing-wise, static is static routing. Dynamic, we're using eBGP, Border Gateway Protocol, to exchange routing information between on-premise and AWS. And then finally, from the authentication point of view, we support pre-shared keys. And since last month and a half, we now also have certificate-based authentication. Today, we're mostly going to focus on dynamic VPN. That's the VPN you want to use for a more complicated environment, as it will react dynamically to any changes in that environment. All right, so what do you need to do to set it up? On the left-hand side, we have a VPC. On the right-hand side, we have our data center. So the first step is to create a VGW, Virtual Private Gateway. It's a managed gateway that is managed by AWS. We take care of high availability, scalability of it. All you need to do is create it and associate it with your VPC. When you create it, you pretty much give it a name and then autonomous system number, ASN, which is a BGP identifier that helps with identifying each side of the BGP connection. The second step is to define the customer gateway. I'm not saying create, because you already have it on premise. The customer gateway is your device. It's a firewall, router, anything that can do IPsec, sitting in your data center, and all you need to do is tell us about it. So you tell us what name you want to give it. Is it going to be used for dynamic or static VPN? Again, what BGP ASN will your side of the connection use? And then finally, what IP address, what public IP address should we expect the connections to come from? Now, there's a new field, certificate ARN. This is where you can use certificate authentication. And as soon as you decide using a certificate for your authentication, you don't need to provide us with the IP address anymore. That is super useful for when you have your device behind the dynamic IP address that keeps changing, or if you plan to change the location of your device, you no longer need to care about the IP address. All you need to care about is that the certificate is right. OK, we have both sides of the connection ready. We click Create VPN Connection. At that point, we provision the VPN termination endpoints, public IP addresses associated with the virtual private gateway. And then your customer gateway initiates the establishment of the VPN tunnels to AWS. And as you can see, one VPN connection is 2 VPN tunnels. Inside those tunnels, we use private IP addresses. We will allocate them dynamically from the 169.254 range, or you can decide what they're going to be. And they'll be used for establishing the BGP peering and exchanging routing information. So at that point, the virtual private gateway now knows about everything on premise. But the instance inside the VPC, by default, it doesn't yet. So the final step is to update the routing table inside the VPC to specify how to get to the on-premise environment. And you can do it 2 ways. You can statically define the route, or you can say that the virtual private gateway should propagate any routes it learns into the VPC. So you can do one or the other. From a throughput point of view, a single VPN tunnel can do up to 1.25 gigabits a second. And even though with the VGW we have 2 tunnels, for traffic going from the VPC back to on-premise, we will typically use 1 tunnel, so you're limited to the 1.25 gigabits a second for the whole VPN connection. Now, with a single VPC, it's simple, but if you have multiple VPCs and you're connecting your VPNs to the VGWs, you need to create multiple tunnels. And then if you add another device on-premise to be redundant on-premise, you're now doubling up on all the tunnels. So with 4 VPCs, we now have 16 tunnels to manage on our devices. So at the end of last year, we've announced the availability of AWS Transit Gateway. The best way to think about a Transit Gateway is a managed distributed router that you put inside an AWS region. It allows you to attach multiple VPCs and create this hub and spoke topology where those VPCs can communicate to each other. But you can also consolidate that connectivity from thousands of VPCs back to on-premise through a single VPN connection. You still need to remember about the routing. So make sure you update the route in the VPC to say that now to get to on-premise, you need to go to the transit gateway first. And then the transit gateway would automatically learn about the routes if you're using BGP. Single VPN connection here, still to VPN tunnels. You still have the 1.25 gigabits a second limit. But the good news with Transit Gateway, we allow you to do ECMP. ECMP, equal cost multipath. It's a mechanism that allows you to distribute traffic across multiple connections and get additional bandwidth. So effectively, you're aggregating the bandwidth of however many tunnels you create. And then if you are setting up high availability, it's now very simple. You add another device that's only 2 extra tunnels, so a lot simpler to manage. So if we compare the two side by side, connecting to a VGW and connecting to the TGW. When you're setting up a VPN connection, 2 tunnels, to a VGW, that's 1 VPC. To TGW, that's 1 TGW, but potentially hundreds of thousands of VPCs. From a throughput point of view, 1 VPN connection, typically 1.25 gigabits a second. With transit gateway and ECMP enabled, 1 VPN connection, 2 tunnels times 1.25, 2.5 gigs. And you can keep adding tunnels. So 2 connections, 4 tunnels, 5 gigs, 3 connections, 7.5. Just one thing to consider, because it's too beautiful to be true. You have to consider costs when you're adding transit gateway into your architectures. Okay, so one other thing to mention is this week we launched AWS Accelerated Side-to-Side VPN. So typically, a VPN connection would run over the internet, and the further away you are from where your transit gateway is, the higher likelihood of issues with your connection. So latency, packet loss, jitter. So the goal of Accelerated VPN is to leverage another AWS service called Global Accelerator that we use for optimizing application performance to now start optimizing the performance of the VPN connection. So if we have a look how that works, we now got rid of our VPCs. We're just focusing on the transit gateway on the left. Traditional VPN, side-to-side VPN connection is going to go local ISP and then a bunch of networks over the internet all the way to where the transit gateway is. And again, every hop potential for performance challenges. With accelerated VPN, straight from your local ISP, we will get you onto the AWS global backbone with terabits of capacity, 100 gigabit Ethernet links, and congestion-free network. So that VPN has a higher chance that the performance is going to be much better than the traditional running over the internet. But if you want to set up without using the internet at all, that's where you would look at AWS Direct Connect. So that's dedicated physical connectivity into the AWS backbone that allows you to get more consistent and predictable performance and reduce bandwidth costs. So with Direct Connect, we always have to think about 2 aspects. It's now a physical construct, so we need to think about how we set up a physical connection, and then think about how we overlay our logical connections on top. So let's start with the physical. We now zoomed out a little bit from the VPC. This is the AWS global network. So imagine these are all AWS regions, except for China, that we want to connect to. So the first thing we need to do is select one of 100+ Direct Connect locations we have around the world where you would be connecting to AWS. Typically, you would pick the location that's closest to where you are, so closest to where your data center is. So maybe our data center, this example, is somewhere on the East Coast. So we're selecting a location in New York, and we're specifying we want 1 gigabit a second throughput. So once we have the location, we will have an AWS router in that location with the port waiting for you to connect within 72 hours. So we're pretty fast. The next step is for you to figure out how to connect to that port. Now, if you're lucky, you will have equipment in the same location. So then it's very simple. Just run a fiber link, cross-connect between your device and AWS device, and extend that connectivity back to on-premise. If you don't have presence in that location, you can work with partners. They will help you extend that connectivity, whether it's a layer 2 circuit all the way back to on-premise, an MPLS network, or any other type of extension. You can just work with partners. There's dozens of AWS partners that can help you do that. From a physical side, you also have the option to create link aggregation groups that allow you to aggregate up to 4 links into a group and distribute traffic across them to get additional bandwidth. In that scenario, you would also be specifying how many links do you want to be active for the whole connection to be considered as up. So in this example, I have 3 links. I want at least 2 to be up for the connection to be active. So if I'm only left with 1 live link and the other ones are down, I want the whole connection to be considered as down. And so far, and throughout this session, I'm going to be showing you a single Direct Connect location for simplicity. But a single Direct Connect location is not a highly available way to connect to AWS backbone. A location has redundant connectivity, but the location can go down itself. Or if you have a single device in that location, that device can have maintenance. So this year we launched the Resiliency toolkit, which is, you can find it in the console, which gives you recommendations on how to set up Direct Connect in a resilient way. So depending on your criticality of the workload. So for highly critical workloads, we would recommend multiple locations with multiple Direct Connects in each location. Okay, so let's go back to our simplified, non-redundant scenario. We have our physical setup ready. Let's start talking about logical connectivity. So we're back to our VPC. We now have our virtual private gateway again. So to connect, we will create a virtual interface, in this case a private virtual interface, that will have a BGP peering session on top. That's effectively a VLAN and a BGP peering session combination from your side. And over that BGP peering session, we're advertising the IP address range of the VPC to you, and you're advertising to the VPC whatever ranges you want. And at that point, communication is happening. You still need to remember to update the routing table of the VPC to be able to get to on-premise. And we have different flavors of virtual interfaces, and they differ depending on what you're trying to connect to. All of them are a VLAN and a BGP peering session behind the scenes. Now, the difference is depending on what you're connecting to. So if you're connecting to a VPC, then you'd be using a private virtual interface. You can do that either directly or use a Direct Connect gateway, and we'll talk about Direct Connect gateway in a moment. If you're connecting to a transit gateway, then you would be using a transit virtual interface, again, through a Direct Connect gateway. And then finally, if you're connecting to stuff outside of your VPC, public IP addresses belonging to AWS, that's when you use a public virtual interface. So let's start with the private virtual interface. So I showed you earlier connecting directly to a VPC. That's not really the best way to do it, because in that scenario, you're limited between the location and a single region, plus you can only connect to one VPC. So if you want to use a single private virtual interface to connect to multiple VPCs, that's where you would use a Direct Connect gateway. And Direct Connect gateway is a global construct. There's no additional cost for deploying it, but it allows you to connect through a single interface to up to 10 VPCs in any region you want, except for China. So you can see here those 3 VPCs we're connecting to are actually in different regions. And then we're advertising through the Direct Connect gateway over the BGP peering that now terminates on the Direct Connect gateway, all those prefixes back to on-premise. From a traffic flow point of view, Direct Connect gateway is not to be used for communication between VPCs. It's only used for traffic going to on-premise and from on-premise. Even if you try to help in traffic through on-premise, it won't be allowed. Now let's look at a transit virtual interface. So in this scenario, we still have a bunch of VPCs, but now we're interconnecting them in each region using the transit gateway. And now we want to connect that transit gateway back to on-premise. So in this scenario, again, we use a Direct Connect gateway. But because we're connecting to a transit gateway, we have to use a transit virtual interface. Still, BGP and a VLAN combo on your side. This time, the transit gateway can advertise up to 20 prefixes to the Direct Connect gateway. So you need to be able to aggregate all of the VPCs hanging off that transit gateway. So you can have 1,000 VPCs. You still need to be able to aggregate the routes to 20, advertise them to the Direct Connect gateway, and then Direct Connect gateway advertises them to on-premise, to your on-premise device. From a flow point of view, again, Direct Connect gateway cannot be used for communication between transit gateways in this scenario. If you need your transit gateways to communicate to each other, then since yesterday, you can now launch cross-region transit gateway peering. So you can connect your transit gateways in different regions and only in different regions, and then allow communication between VPCs in those regions through the transit gateway. Okay, final VIF, public virtual interface. So we still have the VPC there, but public virtual interface doesn't give us access to the VPC. It gives you access to everything outside of the VPC, other services, simple storage services, S3, CloudWatch, DynamoDB, and so on. And public virtual interface doesn't actually go into any gateway. It just lands in AWS, and we will start advertising around 3,500 public addresses belonging to AWS from all of our regions to you. And you have the ability to filter which ones you want to accept. So you don't have to accept all 3,500. You can maybe focus only on a single region. But as soon as we do that, if you're going to S3, your traffic will be using Direct Connect instead of going over the internet. There's an interesting integration with AWS VPN in this scenario. If you remember, the VPN termination endpoints are also public IP addresses that belong to our public address space, so we will also advertise them to you over this public VIF. So if you had your VPN going over the internet, if you have a public VIF, you can have your VPN going over Direct Connect. So adding encryption on Direct Connect and getting the extra reliability. And this applies to a transit gateway as well. So if you have a transit gateway and you have your VPN termination endpoints, public IP addresses again, so your VPN can also go and hit those public endpoints through the public VIF. So let's put them all side by side. So we have a private virtual interface, transit virtual interface, and public VIF. So private VIF, recommendation, use a Direct Connect gateway, allows you to connect up to 10 VPCs. You need an 11th VPC, create another Direct Connect gateway, another 10 VPCs. Transit VIF, single transit VIF can get you to a Direct Connect gateway and up to 3 transit gateways. If you need to span to more transit gateways, today you can probably start setting up those cross-region peerings as well. Public VIF gets you access to all of AWS public services, so everywhere except for China. Okay, so these are different flavors of VIFs. We also have different flavors of connections. So you have a dedicated option. That's where you go to directly to AWS and say, hey, I need a connection in this location. Or there's 2 partner offerings that you go to a partner and say, I need this connection from a partner that already has connectivity to AWS. So a dedicated connection comes as 1 gigabit a second or 10, and comes with 50 virtual interfaces. And they could be private or public. Plus, you get an additional transit virtual interface. So altogether, you get 51 virtual interfaces that you can use on that connection. On a hosted connection, which is provided from a partner, it has different speeds. It ranges from 50 megabits a second, 100 megabits a second, so a lot lower than dedicated, going all the way to 10 gigabits a second. But on that connection, you only get a single virtual interface, and you have to decide what it's going to be. Is it going to be a private connection, private VIF? Is it going to be a public VIF? Or is it going to be a transit VIF? But you can only deploy a transit VIF on a hosted connection of speeds 1 gigabit a second and above. So if you decided to go for like a 100 meg hosted connection, you won't be able to create a transit virtual interface on it. Finally, a final partner offering, hosted virtual interface provided by a partner. You can see we don't have that blue connection container there, as it's only provided as a virtual interface. So you get a single virtual interface, speeds ranging from 50 to 10 gigs again. There's a chance for oversubscription there, whereas with hosted connection and dedicated connection, you get dedicated bandwidth. You don't get oversubscription. But you can't, on the final option on hosted virtual interface, you can't create a transit virtual interface no matter how high you go with the speed. Okay, so these were the building blocks. Let's start gluing them together. So we'll talk about some of the architectures we worked through with some of our customers. So here we have 3 different regions and 2 Direct Connect locations. So it's already looking good. We have 2 locations to Direct Connect, so there's some redundancy at least. And maybe we have multiple VPCs in each one of the regions, interconnecting to the transit gateways, and then we interconnect the transit gateways across regions. So we want to have a full mesh connectivity here, any to any. We want to be able to have a VPC from region 1 to talk to VPC in region 3. And then how do we connect this back to on-premise? Well, we can create a Direct Connect gateway, attach it to those 3 transit gateways, and then use a transit virtual interface on each Direct Connect location and connect it to the Direct Connect gateway. Why is this good? Gives us full mesh connectivity, and it's redundant connectivity as well. So if one of the location fails, we still have connectivity to all 3 regions. Routing in each one of the VPCs is super simple. Each VPC has just one route out to the transit gateway. The transit gateway has to have all the routes, and it can have 10,000 routes to decide how to forward the traffic further. Is it going to another region? Is it going to on-premise? Is it going to another VPC? It's very scalable without you having to do a lot of management overhead. Right? You can keep adding VPCs without making changes to your BGP peering, to your virtual interface. But there's some things to consider. There's a data processing charge on the transit gateway that you have to consider in this scenario. And then there's that limit, 20 routes that each transit gateway can advertise back to on-premise. So if you didn't plan it really well and you have addresses of the CIDR ranges of the VPCs that are hard to aggregate, this could be a challenge. All right, let's look in another scenario. Same setup. But in this case, we use the transit gateways just to allow connectivity between the VPCs. So VPCs can talk to each other in the same region. They can talk to each other across regions. How do we connect this back to on-premise? So we can use the private virtual interface and the Direct Connect gateway to, again, connect to up to 10 VPCs. Once we hit the 10 VPCs, we create another private virtual interface. And on a dedicated connection, you can have 50 of them. Create another Direct Connect gateway to connect to next 10 VPCs. So here we also have nice full mesh connectivity, highly redundant. We don't have those transit gateway processing charges anymore for data going to and from on-premise. And actually, getting data into AWS VPC over Direct Connect, there's no data transfer fees. It's $0. Some considerations here. You have to have some automation. For every 10 VPCs, you have to create another VIF and another Direct Connect gateway. And also, your VPCs potentially have different routes. There's 2 exits now, so you need to make sure that you know how to route to other VPCs and you know how to route back to on-premise. One more scenario. Now looking at adding redundancy to your Direct Connect setup with transit gateway. So we've seen this diagram earlier. This is the single location, non-redundant setup connecting to your Direct Connect gateway. But maybe you're requesting another location, but you want to add some redundancy in the meantime. So what you can do is set up VPN connections from either from your router on-premise or something sitting behind that router to your transit gateways. So what's good about it? It's very simple to set up. Right? It adds that backup that you need in case the Direct Connect has a failure. But there's some things to consider. The VPN doesn't have that 20 route limits as the transit gateway and Direct Connect gateway has. So you might accidentally end up advertising more specific routes over the VPN and attracting traffic over the VPN instead of Direct Connect. So you just need to be mindful of how you configure BGP and what protections you put in place to prevent that. And the other things to consider is VPN can still have 1.25 gigabits a second. So if your Direct Connect was 10 gigs, or maybe 40 gigs because you aggregated 4 connections, they need to make sure you have enough tunnels to match that bandwidth in case there's a failure of your Direct Connect location. So you've seen the transit gateway is becoming this central hub for a lot of the connectivity. So this week we've launched the Transit Gateway Network Manager, which gives you additional visibility and information about your network. So we've heard from customers that once you set up a complicated network, it's then hard to keep an eye on what's going on. So now you can create those dashboards where Transit Gateway is this hub of your connectivity, and then you set up Direct Connect, VPNs. You can overlay your own sites on top of those diagrams as well, and then see live what's going on with your connections. OK, so at that point, I'm going to hand off to Anup to talk to us about Ingress Routing.
Thanks, Tom. Hi, everyone. My name is Anup Devani. I'm Principal Product Manager in VPC team. And I want to take next 10 minutes or so to walk you through a new feature that we launched yesterday called VPC Ingress Routing. Over the last few years, we have seen our customer use cases evolving in AWS. In many cases, our customers have migrated entire data center to the cloud in multiple VPCs. And they want to bring same network and security appliances that they've been using on-prem. In some cases, our customers need to treat traffic in a very specific manner as it comes from on-prem or comes from internet to their VPC. So that specific treatment could be marking the packet, changing the DHCP bit, encapsulating the packet, and things like that. But one use case that majority of customers ask for is more granular access control using advanced firewalls. So with VPC Ingress Routing, we are making it easier for our customers to deploy third-party appliances in the VPC, specifically when you have these hybrid architecture that Tom talked about. Because of the compliance reasons, security reasons, you want to intercept traffic coming in from on-prem or coming over the internet. So my goal here is to walk you through how Ingress Routing works. So what I'll do is I'll take an example. Since access control is one of the biggest use case, let's take an example. I'll walk you through how customers have been deploying inline firewall in VPC today, and with Ingress Routing, how that deployment can become a little more flexible. So since we're talking about access control, one of the things I want to do a quick recap is a universal feature that's used by our customers is security groups. A quick 30-second recap. I'm sure you all know about it. You have an instance in your VPC. It's running an application. You have a user sitting outside in the public internet. This instance has a public IP. User sends the traffic to this instance, to this specific public IP. Traffic comes over internet gateway, and it's actually sent to the instance. And security group on an ENI essentially kind of give that access control where you allow or deny packets based on the port and the protocol. But what we have been witnessing is that our customers are asking for more. They are asking for intercepting this traffic through third-party appliances. Often we call that middle boxes. Some of the common use case that we have heard over the last few years is that we need to have a firewall in between all the traffic coming from on-prem to AWS. Hence, it becomes important for them to have an inline firewall in their hybrid architecture in VPC. For compliance requirement, I want to have an IPS IDS in our VPC and inspect the traffic coming from any untrusted zone like internet. Some customers want to do deep packet inspection, look at the packet, and then decide whether to grant access or not. So they want to take decision based on L7 as opposed to L4. Customers want to deploy an appliance, which is central appliance where all traffic from on-prem or internet actually goes through. And then finally, as I mentioned, the theme here is security, but we have seen very specific use cases from customers where they want to deploy their virtual network functions for some specialized network or security functionalities. Or they want to deploy their homegrown application to treat traffic something in a different manner. So regardless of whether it's a security appliance or a network appliance, Ingress Routing makes it easy to deploy these appliances in VPC. So let's take a quick look at how customers have been deploying an inline firewall in VPC prior to Ingress Routing. So similar setup that we had for security group, you have a user sitting in public internet, you have an instance in the private subnet with a 10.some address, and you have a firewall in a public subnet with a public IP. What happens is that today, customers have to create a route table on their subnet route or in a subnet route table, create a default route saying that all traffic going out of this subnet should go to a next hop, which is the blue ENI, which happens to be the ENI of your next generation firewall. The packet actually goes out of the instance, goes to NAT gateway, firewall. Firewall does the source NATing of the packet and sends the traffic out. And since firewall is doing the source NATing, the traffic coming back from user is attracted to this firewall, or it's actually destined for this firewall. And firewall has the mapping, and then based on the policy, whether it will deny or allow the packet. Now, this is possible today. People have been doing that, but talking to customers and more importantly to our vendors, we have a huge ecosystem of marketplace partners who believe that they want to do functions for which their customers are deploying them for, whether it's a deep packet inspection or for IPS and IDS. They don't want to do NAT functionality because it reduces their performance, and essentially they want to actually focus on things which they are built for, and offload the NAT functionality to a highly available service like NAT gateway or an internet gateway. And this is where Ingress Routing comes in handy. Ingress Routing is a simple yet very powerful feature. What you get with Ingress Routing is that now you can associate a route table with your internet gateway or a virtual private gateway, which means that you can treat these gateways as a true border router of your VPC and actually do traffic engineering. You could say traffic destined to subnet A in AZ-A go to a firewall A, and a traffic going to subnet B can actually go to an appliance B. You can have fine-grained rules, a routing rule which will help you redirect the traffic to an appliance which can be in a transparent mode, which means it won't change the source IP or a destination or IP header information of the packet, and it can do the functionality that you want that appliance to do. So again, this is applicable to traffic coming over virtual private gateway or internet gateway. It helps in many cases to allow customers to bring the network and the security policy that they have been using in their on-prem network to the cloud as well. So let's take a look, how does this work? Similar scenario, you have an instance. This time, this instance is a public IP address and a private IP address. It's in a subnet. You have a firewall this time. This advanced firewall is in a transparent mode. And you have a user in the internet. It sends the traffic. Traffic actually is destined to the public IP of this instance. Packet comes to the internet gateway. There is a routing table, which is called gateway route table, that is associated with this internet gateway. It says that any traffic that belongs to 10.1 goes to blue ANI. Again, our internet gateway is by default a NAT device as well. So it knows that the public IP of 54.xx is actually mapped to the private IP of this instance. So the routing rule that you have defined is you're using the private IP address of that EC2 instance. So the rule says my next hop for this traffic is a blue ENI, which happens to be your firewall. Packet goes here, and obviously the firewall will inspect the packet and allow or deny the packet based on the policy. Now, some of the advantage here is that it works for the both direction, especially for traffic coming in your VPC. When you actually have a NAT device which does source NAT, a lot of time what happens is that the traffic which is initiated by the instance is the only traffic that comes back because the NAT mapping happens on the firewall. But in this case, you can actually seamlessly redirect the traffic which is coming over your internet gateway or a virtual private gateway. So a little more realistic scenario that you would see that we already see customers actually deploying when we did some private previews of this feature is that you will have essentially for access control and advanced firewall in each of the AZs, and same use case when a user wants to access this IP address of 54.x. It will actually send the traffic to this internet gateway. Internet gateway will actually have 3 routing rule in this scenario. And what it's saying is that if my target is an AZC, I want to send it to a firewall which is an AZC, and so on and so forth. So in this case, the packet comes to internet gateway. There is a lookup that happens. This lookup tells the internet gateway that the next hop of this traffic is a red ENI, which happens to be the firewall in AZC. Packet goes here, and so on and so forth. So this is how ingress routing works. Very simple to set up. All you do is you have a route table that you today associate with your subnet. Now, either through console or through API, you can actually have a route table that you can now associate with edge device, and once you associate, it's called gateway route table. So I encourage you to go and check out the documentation. We have a broad ecosystem of partners who have already integrated with ingress routing. There are 19 partners available in AWS Marketplace. They issued their blog and solution briefs and press release to actually give you an idea how you can deploy their appliance in VPC using ingress routing. There are demos. Vendors are showing demo. One of my favorite demo that I want to call out is by a vendor where they've actually integrated active monitoring and a passive monitoring in VPC. By this, what I mean is they're using ingress routing and traffic mirroring to protect their traffic and actually do passive and active monitoring together. The way it works with that automated framework that they have developed is that when the traffic comes in, you divert it or redirect it to a firewall. And if they detect that there is probably a chance that there is a threat in your network, it automatically kicks in the Lambda function. It enables traffic mirroring on all the impacted EC2 instances and send the copy of the traffic to an analyzer, a malware detector, or any tool which can inspect the traffic. You can store the affected traffic so that you can do retrospection analysis of that traffic. And if it's a positive threat that they are able to guarantee, they can actually do a feedback loop and start either close the security groups or have a rule in the firewall which will block that threat. So I highly encourage you to go through the blogs and the solution briefs of the demo. And with that, I'll hand it back to Tom again.
All right. So we have a hybrid scenario. We have our network configured. We have connectivity. The next step is to figure out what we do with DNS. Public DNS is typically simple, right? Everyone can reach public DNS. The concern here is private DNS. So your private zones you might have on AWS, private zones you might have on-premise. And end of last year, we've launched Amazon Route 53 Resolver service. This is coming from the Route 53 team, the team that's built our Route 53 service. And it's focusing specifically on the private use cases, sharing hybrid DNS across different environments. It allows you to create endpoints, allows you to create specific rule sets to decide what needs to go where when you do your queries. So before we start looking at hybrid, let's recap on how we do DNS inside of VPC, private DNS. So here we have a VPC with a private hosted zone, example.aws. And for the instance to be able to resolve that zone, it will send a query to the Amazon Route 53 resolver. It's the second IP address of the CIDR range of the VPC. It used to have different names. Amazon provided DNS, the .2, Amazon DNS. The official name today is Route 53 resolver. Once the query hits a resolver, that resolver has access to all the private hosted zones associated to that VPC. And if there's no private hosted zone, it will forward it to public DNS just to a recursive query. So that works great. What if we have two VPCs? All we need to do is associate that private hosted zone with another VPC. So if it's in the same account, if we go to our Route 53 console, we look at our private hosted zone, we can effectively keep adding our VPCs into the list of all the VPCs that should be able to see our example.aws hosted zone. If you're doing this across accounts, you won't see the option in the console, but you can do the same over APIs or CLI. All right. So now the second instance can resolve example.aws, and we can keep adding additional private hosted zones as we go to whichever VPCs we want. So it used to be a little bit more complicated when we had this connectivity back to on-premise. So imagine in the middle we have our Direct Connect or VPN, whatever mechanism we selected. We still have a private zone on AWS, but now we want our server on-premise to be able to send queries to interrogate example.aws. The challenge here is the .2 IP address, the Route 53 resolver, it will not respond to requests from outside of the VPC. So there's no way for the server on-premise to be able to reach it. So the way to solve it is to deploy a Route 53 resolver inbound endpoint. You always have to do at least two. These effectively are ENIs, so private IP addresses in that VPC. And as long as there's a private hosted zone associated with the VPC where you have your ENI, you'll be able to resolve it. So the server forwards all the queries. So this is forwarding, not delegation. Forwards all the queries to the endpoint. That endpoint is in the VPC that has the private hosted zone, so it can interrogate it. So if we need on-premise to see multiple private hosted zones, all we need to do is add multiple private hosted zones to the VPC where we have the endpoint. What about the other direction? So now we have a private zone on-premise, example.internal, hosted on that server, and we want our instance to be able to resolve it. One option would be to just point our instance to use the server on-premise as the DNS resolver, but at that point, we're losing the visibility of any private hosted zones we have inside the VPC, plus we're adding a dependency on our Direct Connect, so if it fails, all the DNS goes down. So the way to solve it is we want our instance to still be able to use the local VPC DNS, Route 53 resolver, to be able to interrogate any private hosted zones that are associated there. But now we can also add rules. So we can create forwarding rules to specify how a specific query should be treated. So we can say that if the query is going to anything ending with example.internal, it should be forwarded to an on-premise server. And the way we forward this query to on-premise is we need to create another endpoint. This time it's an outbound endpoint that will be used for forwarding that query. So this scales really well across multiple accounts and multiple VPCs. So if we want to share those rules and the capability to use the endpoints, we will use a service called Resource Access Manager. It's a service specifically dedicated to sharing resources across accounts within your organization, outside of your organization. It's used for sharing subnets, used for sharing transit gateways, but it's also used for sharing Route 53 resolver rules and the capability to use the outbound endpoint. So we can share those rules with other VPCs. So that means all the other VPCs will have the same rule set as our primary VPC. So if we have an instance in the VPC on the left that sends a query to www.example.internal, it will hit the forwarding rule. We transport it over our AWS network to the outbound endpoint, and then the outbound endpoint forwards it to the server that is authoritative for that domain. One thing to note here, you don't actually need to have any connectivity between those VPCs for the query to be resolved. We take care of transporting that query all the way to the endpoint. And one other thing is you don't have to create any additional endpoints. All you do is create one endpoint, and then you share the rules with all the other VPCs. OK, so let's talk about remote access. So AWS Client VPN is a managed service allowing your remote users to connect to AWS resources and beyond. So if you have a snow day, if you have a lot of people connecting, we take care of scaling the VPN endpoint up and down to accommodate your users. It also allows you to provide granular access rules, so you can, maybe based on Active Directory groups, decide which users have access to what resources. And it integrates with things like VPC or our Active Directory services. So when you're deploying a client VPN, first thing you need to decide on is the VPC that the traffic or that your users are going to be appearing in once they authenticate and once they connect. So we call that the target VPC. The second step is to create a client VPN endpoint, and that's the target to which the TLS session, the remote access sessions, will be created. And finally, you need to associate the two. So what you're saying here is, if I have someone connecting to the client VPN endpoint, I want them to be appearing in AWS in my target VPC. Finally, we want to set up authentication and authorization. From an authentication point of view, we support today Active Directory services, so we can integrate with your Active Directory. The Active Directory also integrates with Radius for multi-factor authentication, so you can use free Radius, Okta Radius, any Radius implementation. We also support certificate-based authentication, so you can dish out certificates and authenticate your users that way. And then you can specify which prefixes, which ranges are your remote users allowed to access. So when your user is connecting, we will provide you with a profile that you can install on any OpenVPN-based client. So we support here the OpenVPN standard. And that user can then create a TLS session to the endpoint, and once authenticated, appear inside the VPC and access whatever resources you decided to give them access to inside that VPC. But you can do more. So you can allow those users to connect back to on-premise over Direct Connect or VPN. You can allow those users to connect to other VPCs over Transit Gateway or VPC peering, or even to internet resources or public AWS resources. Some of the other functionality that launched for Client VPN earlier this year, split tunneling, which means you can decide exactly which prefixes are you sending over the tunnel and which prefixes you're allowing the remote users to just use their regular exit to the internet. We've added multi-factor authentication with Active Directory. Again, this is the Radius option. And we've added support for deploying client VPN using CloudFormation. So to summarize, we've covered quite a lot. We talked about the options for connecting to and from your VPC using Direct Connect and site-to-site VPN. We talked a little bit about some of the new functionality, like accelerated VPN and Transit Gateway Network Manager. Anoop has talked about the Ingress Routing. We set up our DNS, and finally, we've set up a client VPN. So a lot of those services, pretty much all of those services except for Direct Connect, you can easily get your hands on as long as you have an AWS account. So start playing with it, start configuring whatever you want. We also have some additional resources, some training resources that can help you with training on things like VPC or even Amazon CloudFront, and help you prepare for some of our certifications like the networking specialty exam. All right, so thank you very much for your time. I'm going to stay after the session for any questions. So if you have any questions, come over and chat with me. All right, thank you.